This is Mia, and this is your briefing on the giants of atomic science. Today, we know the atom is not a solid, unbreakable sphere, but a complex, mostly empty space governed by the laws of probability. This shift in understanding didn't happen overnight. It was built through the successive breakthroughs of brilliant minds who dared to look closer at the invisible. We are tracking the evolution of atomic theory, starting from the ancient streets of Greece to the high-tech laboratories of the modern era. First, we look back to the 5th century BC with the philosopher Democritus. At a time when science relied more on thought than experimentation, Democritus proposed a radical idea. He suggested that if you kept cutting an object into smaller and smaller pieces, you would eventually reach a particle that could not be divided any further. He called this hypothetical particle atomos, which literally means indivisible in Greek. Democritus imagined these atoms as small, hard particles that were all made of the same material, but came in different shapes and sizes. While he lacked the tools to prove his theory, his philosophical spark laid the groundwork for everything that followed. For over 2,000 years, this idea remained largely a philosophical curiosity rather than a scientific fact. Meanwhile, the real scientific turning point arrived in 1803 with the English chemist John Dalton. Dalton did what Democritus could not. He used experimental evidence to turn philosophy into a formal atomic theory. By studying how different elements combine to form compounds, Dalton concluded that each element is made of its own unique type of atom. He pictured these atoms as solid, uniform spheres, often compared to billiard balls. Dalton's theory was revolutionary because it established that atoms of a given element are identical in mass and properties, and that chemical reactions are simply the rearrangement of these indestructible units. For the first time, scientists had a mathematical and physical framework to explain the behavior of matter, even if they still believed the atom was a solid, unbreakable object. And then came the discovery that changed everything. The atom was not indivisible. In 1897, J.J. Thomson used a device called a cathode ray tube to prove that atoms contained even smaller, negatively charged particles. We now call these electrons. Thomson observed that these rays were attracted to a positive charge, leading him to conclude that the atom itself must contain these tiny negative bits. However, since atoms are overall neutral, he had to account for the positive charge as well. This led to his famous plum pudding model. Imagine a positively charged sphere, the pudding, with negatively charged electrons, the plums, scattered throughout it. Thomson's work was the first to show that the atom had an internal structure, shattering Dalton's idea of the solid, indivisible billiard ball. The next major breakthrough came in 1911 through the work of Ernest Rutherford, a former student of Thomson. Rutherford conducted the famous gold foil experiment, which provided one of the most shocking results in scientific history. He fired alpha particles, which are positively charged, at a thin sheet of gold foil. Based on Thomson's model, he expected the particles to pass straight through. Instead, while most did pass through, some were deflected at sharp angles, and a few even bounced straight back. Rutherford famously remarked that it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This evidence led to the discovery of the nucleus. Rutherford concluded that the atom is mostly empty space, with a tiny, dense, positively charged center. He had found the heart of the atom. Crucially, while Rutherford found the nucleus, the behavior of electrons remained a mystery until 1913, when Niels Bohr refined the model. Bohr noticed that Rutherford's model had a flaw. If electrons just orbited the nucleus like planets, they should eventually lose energy and spiral into the center. To solve this, Bohr proposed that electrons move in fixed, circular orbits at specific distances from the nucleus, which he called energy levels or shells. In Bohr's model, electrons can jump between these levels by absorbing or releasing specific amounts of energy, but they cannot exist in the spaces between the orbits. This explained why elements emit specific colors of light when heated. It was a more organized, tiered view of the atom that brought us one step closer to the complex reality of subatomic physics. Finally, we arrive at the modern quantum mechanical model developed by a group of scientists, including Werner Heisenberg and Erwin Schrödinger. They realized that electrons do not actually travel in neat, predictable orbits like planets. Instead, the behavior of electrons is much more like a cloud. This modern theory suggests that we cannot know exactly where an electron is and where it is going at the same time, a concept known as the uncertainty principle. Instead of fixed paths, we use mathematical equations to identify orbitals, which are regions of space where there is a high probability of finding an electron. This electron cloud model represents our current understanding, a dense nucleus surrounded by a fuzzy, energetic haze of electrons that are constantly in motion. In summary, the atom has evolved from an ancient philosophical idea of an unbreakable block to a sophisticated quantum cloud. In 1932, a scientist named James Chadwick solved one of the greatest mysteries of the universe by discovering the neutron, a particle that changed our entire understanding of how atoms are built. For decades, scientists knew that atoms had a central core called a nucleus, but the math simply did not add up. They knew about protons, which have a positive charge, and they knew about electrons, which have a negative charge. However, the weight of the atom was always much heavier than the protons alone could explain. Chadwick's discovery of the neutron, a particle with no electrical charge at all, provided the missing piece of the puzzle. Two scientists working separately, Maria Goeppert-Mayer in the United States and Johannes Hans Janssen in Germany, reached the same incredible conclusion. They realized that the nucleus is not a messy pile of particles. Instead, it is highly organized, much like the layers of an onion or the floors of a tall building. Just as electrons orbit the outside of an atom in specific shells or layers, the protons and neutrons inside the nucleus also occupy specific levels. This was a shocking idea at the time because the nucleus is so crowded that people assumed particles would just be bumping into each other constantly, making any kind of organized shell impossible. To understand the shell model, imagine a very organized parking garage. There are a certain number of spots on the first floor. Once those spots are full, the next cars have to go to the second floor. In the nucleus, these floors are called shells. When a shell is completely full of protons or neutrons, the atom becomes incredibly strong and stable. It proved that the particles in the nucleus are following strict rules of motion. Even though the nucleus is incredibly small and packed tight, there is a beautiful mathematical order to how everything is placed. It was a masterpiece of physics that earned Mayer and Janssen the Nobel Prize in 1963. These scientists proved that the universe is built on a foundation of balance and order. For students learning this today, remember that this discovery started with people noticing that the math didn't add up and refusing to give up until they found the missing piece. Whether it is the invisible neutron or the hidden shells of the nucleus, there is always more to discover beneath the surface.